Hey guys, welcome back to the channel. So up until now we have completed several different things like level order traversal, depth height based treating and tree construction and counting the nodes, I guess. Comparison on two trees, path based trees, not so many of them, just two of them. Well, we have to try a few more because this is one tough thing to do. And routed path route to leaf searches and operations. So this was done, it is easy. And then tree leaves, operations on leaves and ancestors. Now we have completed iterative tree traversal. We have three more things like graph creation, DP and BST, I mean binary search tree. Let's see what we learn new. Well, we are reaching the interesting part. Let's see what this graph creation is about. Okay, so let's see. All nodes distance k and bind. So all nodes distance k and binary tree. Okay, lead code medium level problem 863. All nodes distance k and binary tree. Given the root of a binary tree, you have a root of a binary tree. The value of a target node target. The value of a target node. Okay, we have integer value and an integer k. Return any array of the values of all. Return an array of the values of all nodes that have a k distance from the target node. Okay, I guess it's not that simple. So for example, we have 3. If we want nodes, like for example, let's take this as 0 1 and then 2. The distance between 3 and 6 is 2 and k is 2. Then we have to find all the nodes with distance k from 3, 6, 2, 0 and 8. So let's see. Now root is equals to 3. Okay, something, this complete tree, and the target is 5. So we have to select this node and k is 2. And the nodes that are of k distance from 2, sorry, of k distance from 5 are 1, 2, 7, 1, 2, 4 and 1, 2. Well, seems like this is one tough thing to do. Let's see. Before that, let's should log in. This is going to be tough, I guess. Now what should we do? Let's keep a DFS 1, 2. If Let's see the constants too. The number of nodes in the tree is in the range 1 and 500, and the node values will be between 0 and 500. All the values are unique. Target is the value of one of the nodes in the tree. If node dot value left distance LD and right distance RD. So here it is 0. Mhm. 1, 2, 1. Let's keep D, D. Mhm. I have an idea. So the idea is we start with 0 from here, 0 and then 1. Immediately after we reached the target, one, distance distance if if equals to, okay, or return let's see again. We go to the five. Now it shall return 0. First see Oh, I thought so. Something is not. So immediately after reaching the target, we are returning and we are not seeing the next values. Okay. This will give the distance from the root. Six, 1, 2, 1, 2, 3, 4. Sorry, 1, 2, 3, 1, 2, 3, 1, 2, 1, 1. Something is not correct. 1, 2, 1, 2, and here it is 0. So from 5 to 3 it is the distance 1, and 5 to 2, everything above the 5 should be minus and take the absolute value. Like for 2, 2 minus 1 will be 1, and for 4, 3 minus 1 will be 2, 3 minus 1 will be 2, 6 minus 1 will be 2, and for the right side part we'll increment it like 1 plus 2 will be 3, 1, 2, 3, and for 8 1 2 3, for 1 1 2, and for 3 1. We have to use it to our advantage. So I have an idea. Let's keep visit self dot visited equals to false. Now let's print -2 -3 1.0 -3 plus 1. and the target is 2 and k equals to 1. Zero, 1, 2. K minus 1, 2. Minus 1, minus 1. Okay. Y. K is 1 and visited is 2. Oh, minus 3. One. Distance is 1 from the root. Plus 1, plus 1, 2. Well, let's take help from the GPT. Let's see the concept too. Oh, DFS hash table. Well, seems like we are somewhat closer, but let's ask GPT anyway. So lead code 863, right? Hmm. I can. Uh, well, we know what are we assuming wrong. Oh, so, improve. You're actually but if you key it's a viral confusion. Okay. You want all nodes exactly just away from a target node. The trick is that the tree is undirected for this purpose. You can move left, right, or up from any node. So conceptually, this becomes find all nodes at distance k from target in an undirected graph built from the tree. What you did right. You already recognize that you need to track paths or relationships. Your you try to store distance relative to target. You define target and attempted to propagate distance back up. Okay. Your code tries to track distance from target implicitly via recursion depth references differences. But trees don't allow upward traversal naturally. To fully model distances correctly, we need bidirectional traversal, both downwards and upwards. That's why most correct solutions build a graph representation. Parent of node left equal node. Then BFS from the target explores all nodes outwards, one layer at a time, like concentric circles expanding. Convert the tree into a graph. For example, 5 connects to 6, 3, 2. 2 connects to 5, 7, 4. Distance. Oh, well, guys, this is uh, new to us. So let's take a little break and come back so that we'll understand better. Let's not burn uh, our motivation by picking a heavy weight. So easy or like easy ourselves, and let's take a little break and come back again to start this. Well guys, we have to start from where we have left. So let's see what's happening here. We go to, we'll do the DFS, and we had a dictionary parent. Usually the parent will be none, and we'll have all the parents. For every node. Now we'll go, we keep target, target and 0, while this if this not equals to k, let's not append node value, we'll append node value, okay, or else if this is less than k, for neighbors in left, right, in the parent node, if neighbor and if there exists a neighbor and we didn't visit the neighbor, then we add it to the visited set, and then we'll append the neighbor and distance plus 1. So this part is very clean. We have to see what is happening here. We are popping from the left and appending to the right. Sorry. If distance is less than k, then we are checking all the neighbors. For a node, for example, we are taking a node and we have target. We take target. From target we go left, right, and top. We add them to the visited. And we'll append the neighbors and the respective distances to the queue. Now we'll pop another node to check its neighbors. Well, I understood it, so let's try to implement it. Instead of keeping it default dict, now it's not a lookup table, so let's change it to parent, and we don't need instance here. It's not distance, it's parent. Let's keep it num. Now we will record parent of node equals to parent the parent is the previous node. You can keep it top parents. You can keep it on the top. Now let's keep repeated equals to empty set and answer and we'll have a queue. And from target to 0. While queue is not empty. Node distance equals to we pop from the left. If distance equals to k, we append it to the answer. Return an array of the values of nodes. And if dist is less than k, we go through every neighbor from the target. So plus right in the parent node. We'll append the neighboring node and distance It just feels like something is missing. Well, we have a problem. If neighbor exists and if there is a neighbor, then let's run this first. Parents. Okay, 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 okay. We got value. Okay. It seems like this is working fine, so let's submit it. LC. Great. Seems like it is working well, but it is not probably the best answer. Let's see what others did. Okay. Step that up. Okay. And step. Right. Input value. Not putting right value and no value and its left value and dot left value the value. But this might override the right if it has both right and left values. That's new. Difference of this time. Okay, here it is appending. This is the same as ours. Instead of doing it manually, plot like manually, is having all the adjacent values in here itself. Why this is taking more time is DFS takes much time than VFS because recursion will add on the previous data stacks and it will take more time to return, and so it will cause a little delay when compared to the this one, but well, the difference is not very uh, high. So if you say this will take order of n fetches for each node, and here it will take order of n time. Actually, not order of n time, it is the order of k time. So let me explain what's happening here. We're keeping a track of the parents. We're having the parent nodes in this parents dictionary, and with this DFS approach, we are storing the parents in the parents dictionary, parent of each node. After recording all the parents, we are going through a BFS traversal where we keep a set to see if the node is already listed or not, and the answer to return a queue to traverse tree. So starting from the target itself positions as 0. So 0 is the target. Now we'll pop the value from the left and add its neighbors, zeros, the target nodes neighbors to the queue. For example, so target is 5. Now we'll add the target neighbors 3, 6 and 2 to the queue. So if the distance is less than k, if the distance is 1, then in the next iteration we'll return 6, 2 and 3. But if the distance is 2, then we further check, we go further while traversing, we go to 6. It will see if there are neighbors to it. If there are no neighbors, then we forget about it. And to 2, there are neighbors and they are not listed as well. So we add them, like we add them to the queue and we keep them in the visited, and we are already plotting the distance as well. We are adding the distance +1 as we go away from the target node. We add the distance. and we finally return the answer. Let's see here the distance, how we see. Okay, well, he's keeping the distance as well. The stack dot pop is popping from the left, sorry, right, and adding to the right as well. Wait a minute, please. Okay, okay. So we don't need a queue. We can use a stack too. So I hope you guys understood that tutorial. If you like the video, you can share with your friends. And don't forget to subscribe the channel. We'll come up with more engaging content in the future. Thank you for choosing the channel for now. We'll meet you again with another video. Until then, keep learning and keep pushing hard, guys. Goodbye.